Hi everyone, thanks for joining this how-to session on IDS Vision channel. My name is Kevin McCabe, and today I'm going to give you some considerations to think about when setting up a system with multiple UI Plus cameras. Now, why do we want multiple cameras at all? Well, there's a few different reasons, and let's go over some examples first. So here I have a couple examples. On the left, we have an 8-camera system that's set up to look at a waveguide, so catching waves coming in from a bay. And this customer needed a very wide horizontal field of view in order to see the entire waveguide, and they stitched those images together to create that wider field of view that they need. And they use this data, or are using this data, to create some novel wave metrology methods. The center application is a logistics one. In this case, we have 6 cameras with different perspectives. And these different perspectives allow a very complete incoming and outgoing goods inspection to happen. And not only different perspectives in this case, but different perspectives in high resolution as well. And the last example on the right, we have a 6-camera system that is doing some quality assurance. It's looking at wooden brush handles and trying to find flaws like dark spots or cracks or missing chips. And without multiple cameras, it wouldn't be able to see the 2 different perspectives that you can see from there, but also it wouldn't be able to do some depth measurement using stereo vision or stereoscopy. Once you've determined a multi-camera setup could be beneficial to you, of course, more questions come up like, which interface and camera family should I choose? What kind of hardware setup do I need? And how do I handle multiple cameras in software or the API? Well, we'll go over all of these questions and a little bit more in this video. With IDS cameras, we can consider 3 different interfaces for multi-camera systems, and each have their advantages and disadvantages. So USB 3's strength relies on its simplicity. You plug in a camera and it works. And 5 gigabit USB 3 has come a long way in terms of robust components and cabling, interface cards, and hubs. And general PC improvements have made it easy to find quality USB 3 components. That allows USB 3 to be used for multi-camera systems quite well. But we still need to consider the quality of those components a bit more than the other interfaces. A PC will come with a set number of USB 3 ports, which limits the number of cameras you can physically connect to the PC. To increase this, you can use a USB 3 hub. And these typically have 4 to 8 ports, minus the one from the host. And we recommend typically to use an externally powered hub, just to ensure that power isn't a limiting factor. Some cameras can be power hungry and in multiples could go over the specifications of a single USB 3 port. Now, hubs don't provide additional bandwidth. That's because USB's available bandwidth scales with its number of host controllers. One host controller means you have 5 gigabits per second to work with. And typically out of the box, a laptop or a PC will have a single USB 3 host controller, limiting the bandwidth of those ports to 5 gigabits combined. You can add additional bandwidth by using a PCIe expansion card that carries additional USB host controllers. Cards can have multiple USB host controllers rather than just one additional as well. In this example, you can see we are using a 4-port PCIe card with a X4 connection to the host PC. And from one port, we have that 4-port hub, which splits the available bandwidth of that host controller to these 4 cameras. With these 3 cameras that are directly connected to this card, they get the full 420 megabytes a second. And that's because this card has a dedicated host controller per port. Now, USB has another feature called direct memory access as well that drastically reduces the CPU overhead of a USB 3 system. So this can be advantageous when compared to our other interfaces. Now, I'm sure you've heard this line before, but Gigabit Ethernet is a proven and tested interface. It's deployed everywhere in consumer, commercial, and industrial grade equipment. So that means there's no lack of quality components, and the cabling is abundant and inexpensive. And its deployment in data centers and other networking infrastructure have proven its scalability. That means it's excellent for a multi-camera system. On a PC, you'll typically find one Ethernet port, and usually this is Gigabit Ethernet still. Sometimes it's faster, and these are backwards compatible, so that's good. To increase the number of ports, you would use a network switch that's rated for at least Gigabit Ethernet. Almost all switches are externally powered, and some are rated for Power over Ethernet, which allows a single cable to provide power and data to and from the camera. Now, the bandwidth is based on a number of network controllers you have, and a switch does not add any additional network controllers. As you can see, it splits the available bandwidth to all of the devices attached to it. To increase the bandwidth you have overall, you can increase the number of network controllers you have, and you do this with adding a network interface card. These afford you more ports directly on the PC, and in most cases, cards have a dedicated network controller per port. So in this instance, we have the full 1 GigE connection to each camera attached to this card. And cards can be rated for Power over Ethernet as well, meaning you can have a single cable to the camera. 10 GigE carries many of the same advantages as Gigabit Ethernet. There's long cable lengths, proven components, a robust resend, but at 10 times the bandwidth. And even more interestingly, the interfaces are interoperable with each other. So if you want more bandwidth for a multi-camera GigE system, you can use 10 gigabit components. So we have a 10 GigE interface card and a 10 GigE enabled port with at least one 10 GigE port, and it distributes that full 10 GigE connection to any amount of cameras that are attached to that switch. So you could have 10 GigE cameras running at their full speeds. And in this case, when you have a 2-port 10 GigE PCIe card installed, you can even have one additional really high resolution, really high speed camera and a 10 GigE camera too. So which interface to choose? Well, as I said before, they each have their advantages and disadvantages. But most importantly, any of these interfaces are a strong choice for multi-camera systems because there is a robust way in the API to limit the available bandwidth per camera. So you can have a nice stable system with multiple cameras regardless of interface. Now, each interface is better for some cases and others are better for others. There's no denying that. USB 3 would be ideal for lower cost cameras, but higher bandwidth per camera, as long as you can deal with the shorter cable lengths. GigE is ideal for a lower cost option again, and one with many cameras in a multi-camera application. The scalability of network infrastructure is just absolutely excellent. That is, as long as you can deal with lower speed per camera and longer cable lengths. If you go with 10 GigE, you'll have the highest speed per camera and the highest end sensors, and you have that equal longer cable length from GigE. You just have the most expensive option there. So let's say we've chosen an interface, and now we need to choose a camera family or camera model. I've organized our families into 3 different categories, and we'll go over each starting with the bottom. Now at the bottom, these cameras are not the best choice. These are the XLS, the XCP, and the XLE. They'll still work in multi-camera applications, but again, there are a few reasons why they're not fantastic. There is no image memory on board, so as a sensor is capturing an image, it wants to send it straight away to the host. And that means if there's any collisions on the bus, as there can be with multi-camera systems, that image could be lost. In addition, these sensors are MIPI based and have a microcontroller instead of an FPGA as the kind of logic controller on the camera. And this combination means that they are not the most precise in terms of synchronization. So you can have trigger delay time that can vary quite a bit from camera to camera. Not the best if you need synchronization between those cameras. In the middle, we have the LE cameras. And these are a fine choice. They have image memory on board, so they have enough to store some images in case there's a collision on the bus. And they are also FPGA-based cameras. So that means they have that precision needed for synchronizing multiple cameras together. And at the top, we have the best choices. These are the CP FA-SE, and Warp 10. And all of these cameras have the most amount of image memory and are all FPGA based, so you will have that precision needed for synchronizing cameras. With a multi-camera system, you'll likely want some sort of synchronization between the cameras, and this can be achieved in multiple ways. One is via the camera's various inputs and outputs, so hardware wiring them together. Another is with a protocol called Precision Time Protocol for GIGI cameras and 10 GIGI cameras. And at the least, you'll likely want some sort of timestamp when an image is captured from the camera. To get a timestamp of when an image is taken from a camera, you can use a feature called Chunks, which will provide you metadata on images coming in, and that includes a timestamp. To see if your camera has the Chunks feature, you can go to the product page and click the Features tab. Near the bottom of the page will be the Chunks feature, and if it's checked off, the camera supports it. Make sure you're on the latest firmware though. One of our previous how-to videos, hosted by my colleague Phil, called How to Trigger and Flash, will guide you through the process of how to hardware synchronize two cameras. These principles can be extended to more than a pair of cameras. We've placed a link to this video in the description below. GIGI and 10 GIGI cameras have access to a feature called Precision Time Protocol, or PTP. And this is a protocol that allows devices' clocks to be synchronized via a network connection. And it achieves sub-microsecond precision. To employ this technique, I'll refer you to a tech tip on the IDS website called Clock Comparison, and we'll put a link to it in the description below. Now that we're beginning to set up our multi-camera system, we need to know how to handle multiple cameras in the API. And more specifically, how do we open a specific camera? Well, you use the API's device manager object, and you can open cameras by the index of the camera in the device manager, probably the least useful in multi-camera systems because that's just the order of the enumeration of the devices. You can open it by serial number, you can open it by a user-generated ID or string, or you can open it by the IP address of a GIGI camera. So we need to adjust some parameters in our cameras to ensure that we're not overrunning the bus of whatever interface we're using with too much data. We could limit the frame rate, but this really leads to kind of spiky transmissions. The cameras will still want to use the peak bandwidth of the interface that you've chosen. So instead, the real answer here is to use a parameter called device link throughput limit. And this limits the maximum bandwidth that a camera can use. This will limit the maximum frame rate, but it smooths out the transmissions and is a much better way of doing it. Our demo program, Peak Cockpit, has a visual tool to adjust this device link throughput limit and help you get your initial parameters for your multi-camera system. So let's open up our multi-camera workspace and see how it works. So I have two cameras connected through a USB 3 hub to a single USB 3 port. And, well, everything's running fine with a 5 megapixel and 3 megapixel camera. But, well, we're not running anywhere near the maximum speed of either of these cameras. So let's adjust that. If I reduce the exposure time for each camera and crank up the frames per second on both, here we go. Our frames per second down here are nowhere near the maximums that we've set. And if we look at the performance monitor for each camera, I'd say we have a problem here. So let's try to rectify this by limiting the bandwidth to each camera. I'll open the device bandwidth management tool up here and go to USB 3 Vision. And here we have a visualization of how much bandwidth we're using. And yeah, that makes sense. We're way oversaturating one USB 3 port with the maximum bandwidth that these two cameras can push out. So let's divide the bandwidth equally between the two cameras. That's a good place to start. We can also set all camera frame rates to this new bandwidth limit. So down from the maximum to the maximum of the current settings of the camera. And let's start the acquisition. We're still having problems, so we don't have the best hub here. So let's be a little more conservative with our parameters, with our bandwidth limitations. Let's set it down to something like 30%. Let's do 148 on both and set all camera frame rate limits. And from experience, I know these frame rates are a little high usually for the set device link throughput. So let's push them down just to their kind of even numbers, 27 and 46. And let's start the acquisition. Here we go. No more problem, no more lag in the image. We're getting images quickly from the camera, and we have no camera buffers used. Problem solved. So what PC should you buy to solve your multi-camera application? Unfortunately, I have no grand reveal of a PC that will solve all applications the most cost effectively, but I can leave you with some considerations when choosing a system. First, of course, consider the number of host controllers or network controllers built into the motherboard, as well as their speeds. I failed to mention this previously, but a USB 3 10 gigabit host controller can be very effectively used by USB 3 cameras. Consider the number of PCIe slots on the system as well. Typically, with the interfaces that we've discussed here, you'll want at least a Generation 3 PCIe connection with 4 lanes, and however many of those that you need for your application. Now moving on to speccing a CPU. Now most of the CPU's resources are going to be used up by whatever image processing algorithm that you have in your application. There of course will be some overhead, especially with 10 gigabit Ethernet, and potentially also with higher resolution color cameras where you do the color processing or debayering on the PC itself rather than the camera. Now the CPU also, alongside the chipset of the motherboard and how this chipset is implemented by the manufacturer, come into play on very, very high-end systems with many, many, many cameras involved. But you'll need to dig into a lot of data sheets and talk with people to see effectively what you can get out of a high-end motherboard. Now for the CPU power, the real thing that's going to tax your CPU is whatever your image processing techniques or algorithms are going to be. There's still, of course, going to be overhead, especially with 10 gig. And of course, anytime you are doing color processing on a camera or on the host itself rather than the camera. Now, speaking of that, that is another option that you can keep in mind. Most cameras, or most FPGA-based cameras, have the option of doing the color processing on board, but of course that triples the bandwidth. So instead of sending over a raw image, let's say, for example, at 8 bits per pixel, you would be sending each color channel, red, green, and blue, at 8 bits per pixel, tripling the bandwidth. And if you have a sufficiently large application, don't forget, it might make sense to use multiple PCs rather than a single all-encompassing system. If you network them together, you may have a much better and more robust system. Now, this was a vast topic, but I hope this video will prove useful to you in pointing out important factors to consider when designing a multi-camera system. Thanks for joining How to Multi-Camera Systems. brought to you by the IDS Vision channel.